So hello friends. So over the course of next few videos, we will be discussing topics related to quantum machine learning and quantum neural networks. Specifically, we will be discussing this idea about or the topic about continuous quantum variables. Right? So, but I assume that you guys have already gone through some basic quantum mechanics course. So I assume that you already know what is bracket formalism, some basic ideas about linear algebra and all. So in quantum mechanics, we represent or we abstract out an isolated physical system in terms of a complex Hilbert space, such that every vector in this complex Hilbert space represents one possible state of the physical system, right? There is a very minute subtlety here that because these vectors are from this complex Hilbert space, in front of every vector, if you multiply every vector with a phase, right? For say, you can have infinite such possible vectors, basically which are differing from each other with some phase multiplication or some phase factor. But these all possible states, right, will represent the same physical system. Okay. I assume that you guys have already gone through all these basic ideas, and so we can just move on, right? This state formalism represents what we call as the pure state, right? So you have a container consisting of one possible state of the system. For say the system under consideration is a two levels system, which represents for say a spin half atom, where the atom can be either in minus half or plus half spin. Okay. So you have a container which consists only plus half spin atoms, and there is a corresponding ket vector which represents this state of the system. Okay, but this ket vector cannot represent something called the mixed state, right? So for say you have a container now which is consisting of 60% of the atoms are in minus half state and 40% of the atoms are in the plus half state. You cannot have a single vector which represents this mixture of state, right? So to represent such possibilities or such states, we use something called density matrix. Okay, so I assume that you guys have some or have heard before what density matrix is, or in some basic quantum mechanics course. So so there are basically two properties which are important here of density matrix. One is the property of trace equal to 1. Okay, the trace of the density matrix here I represent as rho. The trace of density matrix equal to 1. This is a boundedness property, or like how do I motivate this? It's basically the systems that we will be considering in the course of the next few videos will be that of finite dimensional Hilbert spaces, right? The system can be represented as finite dimensional Hilbert space. For say the two level atom is basically one such example. But there are also possibilities where the underlying Hilbert space can be infinite dimensional. In such cases, the trace won't be obviously bounded. Okay, so this condition is very important in those cases. Okay, another property which is important or which is imposed on the density matrix is that of semi-definite. Right, the density matrix should be semi-definite and it should be self-adjoint. These two properties combined together ensures that you have a spectral decomposition possible for this density matrix. Okay, so what it means is using some basis vectors, right, the basis of this Hilbert space, you can decompose this rho. Okay, so you can write this rho in terms of this basis vectors. The outer product of the bra vector and the rho vector will result into a matrix. Okay, and you can have some linear combination of it which can represent this rho, the density matrix. But what is important here is this coefficients, these coefficients in the this linear sum. Okay, these coefficients should add up to 1, and these are the probability of finding this rho in one particular pure state. Okay, what I mean by that is, for say in this example, right, you have a mixture of spin up atoms and spin down atoms, right? You have 60% of them aligned in upward direction, 40% of them aligned in the downward direction, right? So in that case, these lambda values will be 0.4 and 0.6. Okay, so it basically means that you have 60% of them in upward direction and 40% of them in the downward direction. Okay, and this lambda in general should be greater than or equal to 0. Okay, cool. In pure state can be represented as only a single contribution. So you have just one outer product of a Bra and a Ket vector. In general, a density operator or density matrix is represented as a linear sum, as I already mentioned, of some positive quantities, and their sum should be equal to 1. Okay, so this can be understood as a convex combination of pure states. So you have these pure states, right, as the corners of a convex figure. Okay, and this convex hull, the area inside it, every point inside this is basically a density operator, which is basically a mixed state. Okay, cool. Now, for say your friend comes to you and gives you a density matrix, and that density matrix represents some mixture that he formed. Okay, he prepared some kind of mixture and gave you a density matrix which represents that mixture, and he asks you, can you tell me that the mixture that I prepared, is it a pure state or is it in an impure state? So how can you find it? Okay, so there is this condition called purity check, where if you trace the square of the density matrix, if it is equal to 1, the system under consideration is a pure state, and if it is less than 1, then system under consideration is a mixed state or the impure state. Okay, so we'll go through one specific example where we can illustrate this idea. For say your friend prepared a 2-level system. This 2-level system is a very favorite quantum mechanical system. So we will use this and motivate a lot of ideas in the next videos also. Okay, so for say your friend comes up to you and he has prepared a mixture of 2-level atom or a 2-level system. One possible container consists of this rho 1, which is a pure state, and second container consists of rho 2, which is a mixed state. Okay, now what you do is you use this rho 2, you square it and you take the trace of it and you check if it is equal to 1 or less than 1. Okay, and that's what we do in the next few slides. You square it. Once you square it, you will end up with 4 terms. But what you observe is, because this 0 and 1 are orthogonal states, okay, the inner product of the orthogonal states is equal to 0. So you will end up with only 2 terms. Okay, the product of this, and the product of 1 1 and 1 1. Okay, and the cross products, like cross terms, 0 0 1 1 will be resulting into 0, and 1 1 product into 0 0 will be 0. Okay, so this is what I have written here. The inner product of 0 and 1 and 1 and 0 equal to 0. Okay, so those 2 contributions won't exist. Cool. So you ended up with these 2 contributions only, one which had equal coefficients, 1/4 and 1/4. So you have such a term. Okay, and once you trace it out, you will be ending up with half. This half is is less than 1, and definitely, so this is an impure state or a mixed state, and this specific mixture is called, in literature, is basically called a maximally mixed state. Okay, just some fact. Okay, similarly, once you find the square of the rho 1 or the density operator corresponding to the this pure state 0 0, it will result into this matrix where you have only 1 in one of the diagonal elements, and the trace of that is 1. Again, this is satisfying our condition, right? We had this intuition that this state will be a pure state, so its trace, the trace of the square of the density matrix should be equal to 1, and that's what we got here, right? For this particular case, the rho 1, the square of the trace of the square of the density matrix equal to 1. Okay, and similarly for the other case, the rho 2, you ended up the trace of the rho square was equal to half. Okay, so that is less than 1. So this condition is satisfied, and now you can go to your friend and tell him that one of this container is a pure state and another container is basically a mixed state. Okay.